So let us start. We are discussing on diffusion phenomena, impurity diffusion in semiconductors, and now we will begin from the point where we ended in the last class. That was the dopants. Dopants behavior in silicon we have already discussed. Now we will discuss the different dopants and their advantages and disadvantages, because group 5 elements, phosphorus, arsenic, antimony, those are used as an n-type dopant of silicon, but in some cases phosphorus is used, some cases arsenic is used. There are certain points behind it, and those points we will discuss comparatively, where we will use phosphorus, where we will use arsenic, and where we use antimony in case of p-type dopant. On the other hand, in case of n-type dopants, in case of p-type dopants, we use normally boron, indium, gallium, aluminium, etc. So out of those 4 elements which belong to group 3 element, and those elements has again some advantage, disadvantages so far as p-type dopant is concerned in silicon, and we will see what are those problems. First is aluminium and gallium. Those two material, one of the major problem is they cannot be masked by silicon dioxide. We know during diffusion process the entire surface of silicon is not doped with the dopant, selective portion is doped with the dopants, and other portions are masked by silicon dioxide. Silicon dioxide is a common material for masking in VLSI processing. Now the masking property will be lost if we see that the diffusion constant or diffusivity of the impurity atoms in silicon as well as silicon dioxide are same, or if the diffusivity of the dopant atom in silicon dioxide is more compared to the silicon, then the masking property is lost. That means it will diffuse through silicon dioxide as well as in silicon, equal amount of dopants will incorporate there, and below silicon dioxide the diffusion cannot be prevented. So that is one of the important criteria, and we will always select the dopant materials considering this point, whether it can protect the layer, whether silicon dioxide is a fruitful masking layer for that particular dopant atoms. Okay. So here we found the aluminium and gallium cannot be masked by silicon dioxide. Probably the aluminium and gallium diffuse equally in silicon and silicon dioxide. Another impurity atom is indium. Indiums are not a popular are never popularly used in p-type dopant in silicon. One of the major reason is that the indium is a deep lying impurity in silicon. Since it is a deep lying impurity, so if you want to have very shallow junction and you want to have junction near the surface, then it will pose some problem, because always its diffusion constant may be very large and it's a deep lying impurity in the bulk of the silicon. Next choice is the boron. Boron is very popular dopant atom in silicon for converting silicon into p-type, okay, because it is a group 3 element and it's more practical, and widely used p-type dopant is boron. Okay, and most of the cases you will find either in diffusion or in implantation for p-type dopant boron is used. The reason is clear if you compare with the properties of other dopant materials. Okay. Now we will discuss on n-type impurities in silicon. N-type impurities in silicon are antimony, arsenic, and phosphorus. These 3 dopants are popular in silicon for converting the silicon layer into N-type. So out of this arsenic and antimony, again if we look into details, then we will find in some cases has got some advantage, in some other material has got some another advantage. So here we found that both arsenic and antimony has low diffusion constant compared to phosphorus, and low diffusion constant has got certain advantages also. For example, the layer which is diffused earlier at the early stages of VLSI process, so there normally we choose dopant atoms which has very low diffusion constant. That means the earlier stages, if we use a dopant atom which has large diffusion constant, that means which diffuses as a faster rate, then in the subsequent high temperature processes, it has been observed that that particular layer will out diffuse and lateral diffuse to a great extent, and it will consume a lot of bulk silicon space, and the main advantage of VLSI, that means high density integration of various components, will be lost. So that's why at the early stages of diffusion, we normally use arsenic or antimony for making a layer into N-type silicon. Okay? Arsenic is a better in comparison to antimony. The reason is that the arsenic provides an excellent fit into the silicon lattice compared to the antimony. Although both arsenic and antimony has got lower diffusion constant, but antimony is not favorable compared to arsenic because arsenic has got an excellent fit into the silicon lattice. But one of the problem in arsenic is that arsenic is a poisonous, and you require safe handling of that particular material compared to the antimony. On the other hand, the antimony has low vapor pressure compared to the arsenic. Okay, low vapor pressure is not always desirable. Okay, and these are the comparison of the properties as a dopant between arsenic and antimony. Now if you look into the phosphorus, we have found that phosphorus diffusion constant is same as boron, but the diffusion constant of phosphorus is 10 times larger than that of arsenic and antimony. That means it is a faster diffusion compared to arsenic and antimony. So we can use phosphorus for making N-type layers which are at the surface of the silicon crystal, which will lie at the surface of the silicon wafer. Okay. And phosphorus is a more practical dopant, and it is frequently used. In VLSI, phosphorus is used as base dopant of PNP and gathering agent. In addition to the emitter dopant in case of NPN transistors, phosphorus is also used as a base dopant for PNP transistor, as well as sometimes it is used as a gathering agent. Gathering agent means it is a technique by which you can separate the defects and impurities from the surface. That is the gathering. Okay. So these are the comparative behavior or comparative comparison of the properties of arsenic, antimony, and phosphorus when you select those for diffusion of a particular layer. Now let us concentrate on the actual reaction takes place during impurity diffusion into silicon. And boron has got three sources, namely solid source, liquid source, and gaseous source. In solid source, we found the boron trioxide is a material which is used frequently, and that is B2O3, and the reaction is twice B2O3 plus 3 silicon, it will give 4 boron plus 3 SiO2 at high temperature. Boron trioxide is a powdered material, solid material. If you keep in a platinum crucible inside the diffusion furnace, and if you flow some carrier gas over B2O3, so that gas will carry some of the B2O3 material, and at high temperature it will come in contact with silicon and it will react with silicon, it will form boron as well as silicon dioxide, and the boron atom will diffuse into silicon. Now, during this reaction, a boron skin will form, and which is also known as boron stain, and it will be deposited on silicon, and that particular stain is very difficult to remove in any acid, and for that we have to perform a separate step, and that step is known as low temperature oxidation or LTO. Before driving, we have to remove that stain, otherwise that stain will act as a continuous source of dopant. So to remove that boron stain before driving diffusion, because this stain or the boron skin will form during the pre-deposition diffusion, and that is removed by wet oxidation, and that wet oxidation is normally done at very low temperature. That temperature is 700 to 750 degrees centigrade, and time is about 30 minutes in wet oxygen. And during that process, the boron stain or boron skin will form borosilicate glass, because you see, along with boron, silicon dioxide is formed, and silicon dioxide and boron combinedly it will form borosilicate glass, and that glass can easily be removed in hydrofluoric acid, because hydrofluoric acid is an agent of glass, we know. So that is the advantage of the forming borosilicate glass, so that the stain can easily be removed. Okay. Next one is boron nitride. That is also a solid boron source. Boron nitride wafers or cakes are available from different companies, suppliers, and they are BN 975, BN 950, BN 1100, etc. are named. They are named like that. And these boron nitride cakes are pre-oxidized at 750 to 1100 degrees centigrade for 30 minutes in order to form thin skin of B2O3 on their surface, which serves as diffusion source. Now here also boron nitride first activated. Pre-oxidized means this process is known as activation of boron nitride. And in the presence of oxygen, if you heat the boron nitride for a long time, then a thin layer of B2O3 will be formed at the boron nitride surface. And now this boron nitride cake is kept in close vicinity of the silicon wafer into the furnace, and at that high temperature ranging from 900 or 1100 degrees centigrade. So the boron B2O3, boron trioxide with silicon, it will form boron and silicon dioxide. Same reaction will follow. Okay, and this boron will diffuse into silicon. Okay, if you use boron nitride, then you have to go for the activation of boron, because that activation process, boron nitride, is changed from B2O3. Okay. One of the advantage of using boron nitride, if you keep it in the normal atmosphere for a long time, then it is not hygroscopic in nature. It will not absorb moisture. But in B2O3, etc., is a little bit affinity with H2O molecule, and if you keep for a longer time in normal environment, it will absorb moisture and it will form some different compound with hydrogen, oxygen and boron. So in order to prevent that, better to use boron nitride, which is not so easily damaged by H2O molecule, and you can always keep it at a higher temperature, preserve it at about 250 degrees centigrade. Whenever you need it, you take it from that source which is kept at a high temperature 250 centigrade, then you activate it and then you use it as a source material. So that's why boron nitride is popular compared to boron trioxide. Now I am coming to liquid source. Liquid source of boron is one is TMB, which is known as trimethyl borate, other is tribromide, then gaseous source is the diborane B2H6, and boron trichloride is also a liquid source, it's not gaseous. Now here, if we look into the liquid source reactions, then also you can find then TMB, trimethyl borate, it reacts with oxygen at 900 degrees centigrade and it forms B2O3, means boron trioxide, along with carbon dioxide and H2 molecules, and which are taken out through exhaust pipe. This B2O3 react with silicon, again it will form boron and silicon dioxide, and this silicon dioxide on the surface is just some form of glass, and you can remove it after making the LTO in hydrofluoric acid. Similarly, boron tribromide BBr3, this is also liquid, and if you use boron tribromide, then it will react with oxygen and it will again form B2O3. Whatever form of the source you take, either it is a liquid or solid in different form, either it is nitride in liquid, if it is a trimethyl borate or tribromide, another is boron trichloride, you see, that is 4BCl3, and is a BBr3, it is 4BCl3, that is also liquid, although it is written here, plus 3 oxygen, it will form B2O3 plus 6Cl2, twice B2O3 plus 6Cl2. That means halide sources, which is tribromide and the trichloride, those halide sources are in liquid form and they will react with oxygen, they will form B2O3. Okay. Now if you look into gaseous source, then gaseous source normally used is diborane, which is B2H6, is a diborane, that means a hydride. Hydrides of dopant elements are all gaseous in nature. You will see in case of phosphorus, or also in case of arsenic also. Diboranes are gaseous, and the hydrides are gaseous. In case of boron, it is a diborane. In case of phosphorus, it is a phosphine. In case of arsenic, it is arsine. All are hydrides of boron, arsenic or phosphorus. Now in the gaseous source B2H6 plus 3 oxygen, it will form B2O3 plus 3 H2O at 300 degrees centigrade. And one point I should mention here, that gaseous sources, that is B2H6, hydrides are highly poisonous in nature, and this is explosive also. That is B2H6 is highly poisonous and explosive gas, and this particular gas is never used in a concentrated form. Before sending into the furnace, it is diluted in argon or sometimes in nitrogen, and you see 99.9% argon and only 0.1% or 0.2% is the dopant gas. So a raw gas of hydride, either diborane or phosphine is never used. It is highly poisonous and explosive in nature. So these are all the boron sources and their reactions, and we found that whatever the source is, either solid or liquid or gases, in all cases first reaction is to form to B2O3, boron trioxide, and after boron trioxide is formed, then boron trioxide react with silicon and it will form the boron atom, individual boron atom, and silicon dioxide. These boron and silicon dioxide together sometimes form boron stain or skin, and that is removed before drive-in diffusion by converting the boron skin completely into borosilicate glass, and that is done by low temperature oxidation, which is known as LTO. Okay. Now we will discuss on phosphorus as a dopant. In phosphorus, again we will see the reaction on solid source, liquid source, and gaseous source. Solid source of phosphorus is P2O5, and which is known as phosphorus pentoxide. And phosphorus pentoxide reacts with silicon, it will form the phosphorus atom and silicon dioxide atom. So twice P2O5 plus silicon will give you 4P plus 5 SiO2, and this phosphorus atom will diffuse into silicon, and the silicon dioxide which is formed at the surface, that is removed in hydrofluoric acid. And here, like boron, this phosphorus will not form a stain, and this SiO2 along with few phosphorus atom can easily be removed in hydrofluoric acid. You don't have to go for LTO. Okay, this is one of the difference in the boron glass removal and phosphorus glass removal. During pre-deposition, the phosphorus glass is completely formed, but in case of boron, during pre-deposition, the boron borosilicate glass is not completely formed. For complete reaction, you have to go for LTO or low temperature oxidation. Here you don't need that particular step. Now, P2O5 is hygroscopic in nature. That means it absorbs moisture. So P2O5 is not used. Sometimes solid boron source is formed by hot pressing ammonium monophosphate with organic binder, that is NH4H2PO4. That is again in the form of a cake, thin slice, and its diameter should be equal to the wafer diameter. And if you, by hot pressing, if you form that solid source, and then this solid source is kept in the close vicinity of the surface of the wafer, and the same reaction will follow. Phosphorus pentoxide decomposes and phosphorus will evolve, and those phosphorus atom diffuses into silicon, and silicon dioxide can be removed in hydrofluoric acid. Gaseous source of phosphorus is phosphine, and is pH3. Again, it is a hydride of the dopant pH3, and like B2H6 means diborane gas, the phosphorus solid gaseous source, that is phosphine, is also toxic and explosive in nature. It's highly toxic and explosive, and so you need dilution of the gas before you use into furnace for diffusion. So here reaction is twice pH3 plus 4O2 will give you P2O5 plus 3H2O, and this P2O5 again will react with silicon, and it will form phosphorus and 5SiO2. And here also subsequent reactions we will see. First, whatever form of the source is, either in the gaseous, or if it is a liquid, then it will be halide. In a halide of the phosphorus atom is POCl3, we will see it, and that has to be converted initially to phosphorus pentoxide P2O5, and then that P2O5 now with silicon at high temperature, it will form phosphorus individual atom which will diffuse, and silicon dioxide which will form as a glass, which easily you can remove by hydrofluoric acid. So now if we see the liquid source of phosphorus, it is a phosphorus oxychloride POCl3, and the reaction is shown here. This 4 POCl3 plus 3 oxygen, again it will form P2O5 plus 6 Cl2, and it is in the this reaction is in room temperature also it can take place, that is within 0 to 400 degrees centigrade. POCl3 in oxygen, it will form P2O5 6 Cl2, and this P2O5 again decomposes to phosphorus, and it will react with silicon to form silicon dioxide, just like the reaction of P2O5 and silicon. Okay. Now, all the liquid source require some bubbler, and the bubbler arrangement is shown here. A typical bubbler arrangement is shown here, and because if the source is in the liquid form, then how the liquid form is brought near the surface of the silicon? Obviously, it has to be in the form of vapor. So that liquid source POCl3, first you have to vaporize it, and the POCl3 vapor will flow into the diffusion tube, where it will react with silicon to form the phosphorus atom and silicon dioxide. And in the diagram you can see that some gas flow arrangements are also kept, and MFC is known as mass flow controller, so that can regulate the gas flow into the bubbler or into the diffusion chamber. And after the MFC, you can see some valves are there. Different gas will have different path. This is the oxygen gas flow path, and nitrogen is here. Similarly, you can use the argon gas flow path, or sometimes you require nitrogen and some other dopant gas flow, etc. Anyway, the nitrogen is flown, you see, into the POCl3 bubbler, and the bubbler is kept in a bath, and that bath is used to maintain a constant temperature of the bubbler. If I maintain the bath temperature at a particular temperature, and if you dip this module, that means the container of POCl3, into this bath, then it will attain the temperature of the bath. And now these are different valves, and if, for example, this valve, bypass valve, is closed, and you open this valve and this valve, then the nitrogen gas will flow through this path into the bubbler, and it will bubble through the gas, and when it will flow, it will carry some of the POCl3 vapor along with it, and this flow, this POCl3 and nitrogen will flow into the tube through this path. And if you want to close it, then you close this valve and this valve and open this one, so that nitrogen will directly flow from this path to this path into the tube. And this, all these connection, all these outlets are connected to the diffusion tube. Okay. So now in this way, the bubbler arrangement is an essential arrangement for liquid source. Okay. Now, normally for POCl3 diffusion, we keep the temperature of the POCl3 container at 0 degree in our case. That arrangement is there in our laboratory, you can see it. And before diffusion starts, we pour the bath with ice, lot of ice, so the temperature will be 0 degree, will maintain. The reason is that at 0 degree the POCl3 will have certain vapor pressure. If you increase the bath temperature, then the vapor pressure also will increase. But for standardization, we maintain the bath at a constant temperature, so that when we repeat the process, we will get repeatable result, because the vapor pressure of the POCl3, we keep it constant at certain value, and that vapor pressure is dependent on temperature. Is a very easy to keep the temperature 0 degree, because easily you can use some ice and it will attain the ice temperature. Okay. So that's why in our laboratory we use ice bath for POCl3 diffusion. Now we discussed about arsenic. And arsenic solid source is arsenic trioxide, As2O3. It has got also liquid spin-on source, which is arseno-siloxane in organic binder at 250 degrees centigrade. It forms arseno-silicate glass. That's why it is known as liquid spin-on source. Gaseous source of arsenic is arsine, which is AsH3, and the reaction is just like earlier cases. You see As2O3 plus 3Si, it will form SiO2 plus 4As at high temperature inside the furnace. This arsenic atom, individual arsenic atom, will diffuse into silicon. That is, solid source is As2O3. Liquid is spin-on source in case of arsenic. Here we don't use bubbler. Just like photoresist to spin, similarly this high viscous liquid spin-on source of arsenic is sprayed over the silicon surface using a spinner, and then it is baked, and then we put the wafer inside the diffusion furnace for arsenic diffusion. And the reaction is again from the spin-on source. First As2O3 will form, that is arsenic trioxide, then it will react with silicon, and silicon and As2O3 will form SiO2 and As, and the SiO2, after pre-deposition is over, you can remove it in hydrofluoric acid. Easily you can etch SiO2. So in gaseous source, arsine gas is used. Again, arsine is a hydride, and it is also highly poisonous and explosive gas. That's why arsine is also diluted before you use it in diffusion furnace. And dilution is must before use, and about 98 or 99% is the carrier gas, which is nitrogen or argon, and the point less than 1%, sometimes 0.1, 0.2% arsine gas is mixed with the carrier gas, and that is used as a dopant gas. Now, for NPN BJT with arsenic emitter has better low current gain. Arsenic has advantages over others is like this. So that has NPN BJT with arsenic emitter has better low current gain, and also arsenic is more frequently used for source and drain diffusion of N MOSFET. What is the reason? Because arsenic, you see, has got low diffusion constant, so automatically the lateral diffusion and also vertically deep diffusion will not take place. And nowadays all the CMOS process are very shallow junctions we are going to form, and in that case we have to choose certain dopant which will have lower diffusion constant, so that it will not consume lot of space in silicon, isn't it? And you can achieve the high density. So that's why sometimes arsenic is preferred over phosphorus for source and drain diffusion in case of N MOSFET. So these are all about the reactions with silicon to get individual dopant atoms. Now we will discuss on high concentration effects. If the dopant concentration exceeds a limit, and that limit is nearly 10 to the power 20 per cc, so then some effect we will see in case of arsenic or phosphorus or in boron, and we will see those effects and its adverse behavior or its anomalous behavior in silicon. So in arsenic, when Nd is greater than 10 to the power 20 per cc, it has been observed that the measured profile of arsenic shows a nearly flat portion near the surface region. Arsenic diffusivity is then expressed as the arsenic is equal to twice Ni, N by Ni into DIAS, where Ni is the intrinsic concentration and N is the dopant atom concentration. Nd is the donor concentration, which is basically here N, and DAS is arsenic diffusivity, and DIAS is arsenic diffusivity in intrinsic carrier concentration. DIAS, the arsenic diffusivity in intrinsic level. So now DAS is equal to twice N by Ni DIAS. Now if you increase N, that means doping concentration is greater than 10 to the power 20, then we will found DAS increases. That means diffusivity increases in case of arsenic. So arsenic atoms form cluster when the concentration exceeds 10 to the power 20 atoms per cc. In case of boron, it has been observed that the diffusivity of boron in a high concentration region reduces considerably, almost to zero. If the boron concentration is more than 10 to the power 20, in the range of 10 to the power 21 or something like that, then it has been observed that boron diffusivity reduces considerably, and sometimes it may reaches almost near to zero. So those are the high concentration effects of arsenic and boron. Now we will discuss high concentration effect of phosphorus. So anomalous behavior of shallow phosphorus diffusion has been observed. That is, in case of phosphorus, if the doping concentration is extremely high, then the normal pre-deposition doping profile we never see, we never get, and rather the doping profile is similar, not similar to the error function diffusion, and some difference is observed, and this difference is like this. You will see at the surface a flat region, and then a kink region, then a broad tail. In case of high concentration diffusion, in the depth of 0.5 to 1 micron range, an anomalous behavior of the doping profile of phosphorus has been observed. What is that? That is, a active phosphorus profile looks like an initial flat top region followed by kink at around 10 to the power 20 per cc, and then by an extensive tail beyond this point. Small fraction of phosphorus is electronically active at high concentration region. Actually, electronically active phosphorus atoms diffuses into the silicon. So if we plot the electronically active phosphorus atom versus depth, then we will see this anomalous behavior, and that anomalous behavior is something like this. Here you can see the curve. You see this is the depth in micron, and this is the concentration, and this is phosphorus, electronically active phosphorus atoms are plotted here, and this is the high concentration region near the surface, as I mentioned, the near 0.5 micron region at the surface. So there you can say a flat region. After that flat, you can find a kink region. This is the kink region, and then a low concentration region, a tail region. This is known as a tail region. Normally in pre-deposition diffusion is a constant source diffusion, you normally get the error function profile. It's not similar to error function profile, something different, and that has been observed in case of phosphorus, not observed in case of arsenic or antimony. So the flat region, next a kink region, and a broad tail. That is the difference with normal arsenic pre-diffusion profile or antimony pre-diffusion profile. The anomalous feature can be explained by considering phosphorus interactions with vacancies in the silicon lattice, which bring about enhanced diffusion effects. Pair dissociation mechanism is seen in case of phosphorus diffusion also. The interaction with vacancies in the silicon lattice that brings enhanced diffusion effects. That is the reason for this anomalous behavior. And in the diffusion profile, experimental profile also shows this sort of nature. There is some flat region followed by a kink. I will show in the next view graph some of the diffusion profile. There also you can observe that. The concentration here which is plotted is the electronically active phosphorus atom, not the total phosphorus atom. Okay. Now, another high concentration effect is band gap narrowing effect. What is that? So, band gap narrowing effect is that if you increase the dopant atoms excessively in the range of 10 to the power 21 per cc, then the band gap of the silicon will not remain constant. That will change. It has been observed that at high impurity doping concentration, the energy band gap will deviate from its original value. This effect is due to misfit strain effect attributed to the phosphorus diffusion in silicon at high concentration, 10 to the power 21 per cc. Strain effect, and this strain is the result of mismatch between phosphorus atom and silicon lattice, as the radius of phosphorus atom is smaller than that of silicon. Because if the substitutional diffusion, silicon atom is replaced by the phosphorus atom, and phosphorus atom radius is smaller than that of silicon, then obviously it is not exactly fitted into the vacancy and a strain will form. And because of the strain formation, it has been observed that band gap is going to change little bit. For ion implanted layers, an additional cause of stress in silicon lattice is from ion implant damage. In normal phosphorus diffusion, we found that strain is formed, but in case of ion implantation, we can see a stress is also formed because of the ion implant induced damages. Because of the strain and stress formation, the band gap will be narrowed, and that is given by this relation. Ni effective is equal to Ni exponential minus delta Ag by 2 kT. That means if delta Ag smaller, it's narrowed down, then what will happen? Ni effective will increase compared to Ni, because it is exponential and with negative. Okay. So because of this, the band gap narrowing, the effective concentration, means doping concentration, will also change. That is the ultimate effect of high concentration of phosphorus in silicon. This is known as band gap narrowing effect. Okay. Now, I will show you some of the diffusion profile. Here, you can see the concentration profile in the intrinsic region of NPN transistor of ECL gate array chip. This is the concentration profile of an ECL transistor, and here you can see this is the emitter region, this is the base region, epitaxial region, and buried layer region. I hope you remember the intrinsic region. Do you know what is intrinsic region? I can show you here in the diagram. You see, now here if you see here, this is the emitter region, and this is the emitter base junction, and this is the collector base junction. Intrinsic region means just across the active region, that means the emitter and below the base, and then collector, and then buried layer. Okay. And here is the emitter, you see the phosphorus, and some sort of, you can, have you observed some sort of kink is here, small portion here, it's not exactly smooth, so it is some kink has been observed here. So then this is emitter base junction, then P base is here, then collector base junction, then this is N neutral epitaxial layer, and then the buried layer, N plus buried layer, and then again you will get a junction, that junction is buried layer to substrate junction, and that junction will be obtained at 9.42 micron depth, and this is up to 6 micron depth. This is the doping concentration. You see here the surface doping concentration is 10 to the power 21, that is the phosphorus doping, and this is of the order of 5 into 10 to the power 17. This is the peak base doping, and in epitaxy that doping concentration is very close to 5 or 6 to 10 to the power 15. That is the epitaxy doping. There is uniform doping, and buried layer, you see buried layer has become widened because of the out diffusion and impurity redistribution, and this buried layer peak concentration is again of the order of 5 into 10 to the power 18 to 10 to the power 19 in that range. This is the typical doping profile of an NPN transistor, and this here is one junction, and this is another junction. That has been, this is a simulated doping profile using Supreme simulator. Okay. Now few other doping profiles we will show you. This is one dimensional plot, that means just vertical depth is x and the doping concentration across the vertical depth. This is the profile. Now I will show you some 2D plot, that means along x and along y, so that you can see the lateral diffusion process also. Now this is the profile of a line source diffusion. A line source is here, it is mask, diffusion mask is here and here, and this is the line, and that is a cross section. That's why it is a small window you can see. If you see the top layer, then it is basically a line, and in this line source, this is iso concentration contours. The 0.5 is n by n surface. N is the concentration divided by n surface is the surface concentration. That is this value, this C2. That means 0.5, if you see the contour, it looks like this. Similarly, 0.1 contour is similar to like this. 0.01 contour is like this. 0.001 is again like this. This is a 2D. X-axis is, you see here, the x is the vertical depth, so that is x by 2 root dt, and the lateral side is y by 2 root dt. So that means 2D iso concentration contours at the edge of diffusion mask is like this. Iso concentration contours means everywhere it is 0.5, and what is this value? This is the C2. C2 is the n divided by n surface. Concentration at that point divided by n surface. That is 0.5. That means whatever the surface here, half of the concentration is here. So along this line you will get half concentration of the surface. Similarly, along this line you will get 0.1 1/10 concentration of the surface at this contour. And this doping profile is given by nRT equal to delta by twice by dt e to the power minus r square by 4 dt, where delta is the impurity per unit length of the slot. This is the slot. Okay, that is the doping profile for line source diffusion. Similarly, if you look limited source diffusion, the doping profile is like this. Here, limited source diffusion, that means at the surface source is limited, and again this is a 2D profile. X is the x by 2 root dt and y is y by 2 root dt, and again iso concentration contours for different C2 at the edge of the diffusion mask. You can see here C2 means n by n surface for 0.9, 0.75, 0.5. You see, if deeper, if you go into the along x direction, then obviously the C2 value will go down, and these values are like 0.9, 0.75, 0.5 like that. This is the iso concentration contours for different C2 values. Another profile is something like this. This is fixed surface concentration diffusion. And here also iso concentration contours. And here you can see lateral penetration is of the order of 75 to 80% of xj. Okay. With this, let me stop here.